Okay, I think we can get started now. Welcome everybody again. This week's session will be all about patch and voltage clamp within Signal. I would say probably about a third of people who use Signal are doing this sort of work. It's one of the main areas that Signal was designed for. If we start just by looking at the sampling configuration, we're going to set up for a basic voltage clamp experiment. Let's we take a look at the sampling configuration. We're going to need a couple of ports. Let's start with, we'll use a basic mode to start with. We're going to use one state. For simplicity at this stage. Sampling at 20 kilohertz here for 1 second, and we're going to sample on 2 ports. If we look at the port setup, we need a couple of channels to define what we're sampling. I can load one I did earlier. Make tradition demonstrations. We'll see here we've got 2 ports that we're sampling on. We've defined the range, the scaling, and the units for these channels. When you're working out the scaling, what we need to work out is what current or voltage at the electrode would be required to produce full scale at the ADC input. Now, I'm using an Axon amplifier here. They use a 10 volt range. So I've configured the 1401 to have a plus minus 10 volt range to match. And it works out that with the gain on the amplifier set to 1, the hedge stage alone will produce 10,000 picoamps are required to reduce 10 volts at the 1401 input, and 200 millivolts would produce 10 volts at the 1401 input. Now that's just with the voltage gain set to 1. What we can do is, rather than work out what it would be for any other particular gain on the amplifier, which we can have have Signal automatically adjust the gain. If we change the gain on the amplifier, it will automatically change the range defined in the software. And there are a variety of ways of doing that depending on the type of amplifier. The amplifier I've got here is an Axoclamp 200B. That is one of many amplifiers that use an analog telegraph. That is, there is a voltage output from the BNC on the amplifier, and that voltage corresponds to a particular gain from the amplifier. So I select the channel that is the output from the amplifier I'm going to be using to sample that output, and click on the 41 telegraphs key. I can set up here what voltages correspond to what gain. I can enter a voltage and the gain, and just keep adding pairs of values to the table underneath. Now, unless anybody's brought out a new amplifier we don't know about, the chances are that we already have a set of table of values for you. So having selected that port 0 is the port we want to scale from, and port 3 on the 1401 is the ADC port we're going to use to sample the telegraph signal. Now, the telegraph signal can't be a port that we're already using for something else. It has to be a separate port. So having done that, we click on Generate Setting from Known Amplifier, and we get a list of amplifiers we can choose from. And when we select that, what we get is a list of values automatically for us generated. So now, during the experiment, if we adjust the gain on the amplifier, Signal will automatically adjust to match that. and so that the values that we see will still be in the correct units, even if we change the gain during the experiment. The ADC for the telegraph is only read between frames, so it won't obviously correct automatically halfway through a frame. If you've got a very long frame, it'll just be incorrect for the second part of the frame until the next frame starts. There are other telegraphing systems with other amplifiers. For instance, the Multiclamp 700 has its own telegraphing system. That's not an analog telegraph, that's a digital telegraph that's done in software within the PC. The Multiclamp 700 is controlled from the PC via a USB lead to the amplifier, rather than by sets of knobs on the amplifier, as you may know. And so if we had a Multiclamp 700, for instance, we would click on the appropriate button. As you can see, we can control, or we can telegraph with up to 4 amplifiers. It's important to realize that we're not, from Signal, we're not setting anything in the amplifier. We have a passive role in Signal. We're reading what the amplifier has been set to using other software. Now you would enter the serial number of your amplifier here, so Signal can identify it correctly. And if we enter the number here, I'm just going to make something up for now. I don't have the 700 here with me. Having entered the serial number, we can now identify what we're going to use on the amplifier. 700 has 2 outputs, a primary and a secondary. They can be configured to supply either membrane voltage or membrane current, and there are probably other settings as well, but those are the 2 that we would most likely use. And we specify which ADC port on the 1401 those outputs are connected to. So for instance, here we've got connected the primary of the 700 onto ADC port 1, and the secondary onto ADC port 0 on the 1401. And we've taken the external command input and connected that to DAC 0. This allows Signal to automatically communicate with the amplifier, so that it can read in what the gains are on those channels and the units as you change them elsewhere. You would be changing them not with Signal, but with Axon's own software, the Multiclamp Commander. I have it running here. I have it running in demo mode. I have seen it done where people haven't realized they're running in demo mode and wondered why nothing was changing. So again, with Multiclamp Commander, you would supply a serial number to that, and it will know then which amplifier to talk to. And you can see we have primary output here is set to membrane current. That can be changed, as can we've got the secondary output, which I've set to membrane potential here. And you can see there's a list of different things we could set that to. These being the 2 most commonly used. So that will be telegraphing with that. If you had a Multiclamp Commander set, I'm just going to unset this one because it could get very confused without one set. But having set it in there, when you come to the clamp tab in Signal, you see you have an MC700 button here. You can click on and you can read what you've got set on the amplifier. So getting the units and the initial scaling is correct. And having done that, once you're running your experiment, as you adjust the amplifier using Multiclamp Commander to change the gains, it will pick up automatically in Signal. So having set up the gain these are the values as if the gain on the amplifier were 1. So just the amplification from the head stage here. And we double click on a port, you can type these values in here and give it a name, and that will be the name of the channel in Signal when you come to sample it, just as a reminder of what you were sampling. You can see that I can't use port 3 because I've specified that as the analog telegraph port for port 0, so I can't use that for anything else. I'd also need to set the DAC, so I've enabled the DAC and set the DAC to the number of millivolts stimulus that I will produce if I provided 10 volts on the input of the external command input. So also on the clamp tab, we have this clamp setup area. This is used mainly for online membrane analysis, measuring membrane resistance, membrane capacitance. And first of all, you select the type of clamping experiment you're doing. And again, you'd say that these are the channels that we're going to be using for sampling the outputs from the amplifier. Notice these are CFS channel numbers. These are data file channel numbers and not the 1401 port numbers. So although we've got the current being sampled on ADC 0, that will appear in the file as channel 1, and similarly for the membrane potential being sampled on port 1, is appearing as channel 2 in the file. And also specify which DAC I'm using to stimulate with. You'll note if I get any of these values wrong, it turns red. This will indicate that the units are incorrect. So it knows the units I set for that DAC. It knows I'm doing a voltage clamp experiment. And it's not seeing that those units are meaningful if I'm doing a voltage clamp experiment. And if I change it back again, it shows the correct units. And similarly for the other inputs. Now you would, if you're planning to do membrane analysis, you best specify a particular state in which you're going to do the analysis. And that's what this check this box here is for. I will come back to this when I demonstrate the membrane analysis online. At the moment, I just want to illustrate the telegraph working when I sample with voltage clamp. So we're all set up. If we just look at the pulses I've defined, I've only got one output on the DAC, and we've got simple square wave that's being output, and it's being stepped up by 10 millivolts each time for 15 times, and goes around again, starts the sequence again. So when I run that, trigger off and run, you can see it's not very exciting. I've only got a model cell on at the moment, so we've got this square stimulus pulse being provided and shown at the bottom. It's a good idea to sample the stimulus pulse, even though you may not be analyzing it as such, but it serves as a record as to what stimulus you used to produce your response at the top. So at the moment it's not very exciting, but what I wanted to show you, if I just stop that a moment, in fact I don't need to stop it, let me go into the pulse controls. So whilst I'm sampling, I can actually change this pulse. I don't need to stop as such. I can delete that one and put a different one on. Let's just put fixed amplitude one this time, just 100, and that one 500 long. Apply that. You see now we're just stimulating a fixed amplitude pulse. It's no longer stepping up in amplitude. Now, if I double click on any axis and say show all, what I'm seeing here now on the y-axis is the full range of the ADC. That is as much as it can be sampled. If you sample outside that range, it will clip. And if I turn the gain up on the amplifier, you see as I turn it up, you get a glitch. But thereafter, the curve looks exactly the same, even though I turn the gain up on the amplifier. And that's because I'm using the telegraphing signal nose. I've turned the gain up on the amplifier, so it scales the data appropriately as it comes in. And what I need, if I now double click on the y-axis and say show all, you see I get a different range. What you immediately notice is that the holding potential is producing a current which is clipped. If you hadn't noticed it was clipped, what you would notice later on, when you zoomed in on that, is that it remains completely flat, even though I'm zooming in. And you can go in as far as you like and it will still be completely flat. Because it's clipped, it's set to the limit beyond which it's the true value is actually beyond the limit, but it can't represent that, so it just sets it to the limit. So which is why it appears to be completely flat. If I zoomed in on a signal that hadn't been clipped, as I got closer and closer, you start to notice the noise appearing on that channel. So that'd be a giveaway that you clipped it by turning the gain too high. Similarly, if you have the gain too low, when you say show all, what you'll get is a flat line, what appears to be a flat line across the middle of the display. And as you zoom in on that, you'll notice it's quantized. You'll see the quantization in the levels because it's digitized and there's a limit to the accuracy you can show. The same number of bits are used to represent the full range of the ADC. So if you're only using a small portion of that range, you'll only be using a few bits to represent your signal. So you won't have the same amplitude resolution that you would if you'd amplify the signal more. The ideal is to have it amplified such that it does not clip, but does use as much as possible of the ADC range to allow a maximum resolution on the amplitude that you've sampled. And if I keep going on that, I'm going to turn the gain back down. And show all. It is possible to use the preferences actually to change its behavior when changing the scale. So maintain display on the y-axis online. So maintain pitch showing all the range, or maintain the ADC range as a percentage of the range. So for instance, if I selected that and applied, when I change the gain on the amplifier, the limits on the axis change rather than the axis staying the same. So if you wanted to get the optimum ADC, optimum gain, you could do show all here and then just up the amplification until it was occupying as much of that range as possible, just to get the best use of the ADC. So that's a basic voltage clamp setup. Look at the basic current clamp setup. This actually looks very, very similar. Just put that and look in the sampling configuration. You notice the DAC this time is being calibrated in picoamps. And the port setup, we're looking at what we're measuring is the membrane potential. So that's the one that's got the telegraph on it this time. And there's a fixed gain for the stimulus, which is now in picoamps. And again, the clamping, I've had wholesale current clamp, and it's checked the units on each of these channels and on the DAC to make sure that they're meaningful for a current clamp experiment. And so now, if I look in more detail at the membrane analysis, show you what I've got here. I've got a single state, not, well, sorry, it is multiple frame states. We've got it's set up for voltage clamp, and we've got 3 states, the basic, and then we've got state 1, which just contain a simple square wave, which is increasing in amplitude by 10 millivolts each time. I can give that a label. Just to show that that's the one that's increasing. And if I go to state 2, here we've got just a single pulse with a fixed amplitude. And this is the state we're going to use for the membrane analysis, because that's going to produce a nice repeatable result. And I can give that a label. Just to indicate that that's the pulse that's not going to increase. When I run, just need to check that I've got the voltage going in on ADC2, ADC1, sorry. And let me just move it around. And that hopefully, okay, basic is the one that's not stimulating. I can do the increasing one. Now this isn't going through the amplifier. What I'm put instead, I've put an RC circuit on, just because it illustrates the capacitive transient a lot better. And what I will then do, if I go to the membrane analysis dialog, see it switches to state 2, which is the state I'd specified as my membrane analysis state. And it fits a double exponential to the capacitive transient and takes readings from it. And using that to calculate, here we've got the total resistance, the access resistance, the membrane resistance, an estimate of the membrane capacitance and its time constant. I can also adjust the holding potential from here, and I can take an average of these readings rather than taking it every time. What I've got at the bottom here is a scrolling display of a particular reading. So in this case, it's the time constant, and that's scrolling across. I've got 20 readings on this display at the moment, going across the screen. If I increase that to 200, it scrolls a bit slower and you can see what's happening. Now, if I adjust the capacitance, I've got the variable capacitor on here. You can see how the capacitance changes there, and that's reflected down at this display at the bottom as the capacitance goes up and down. All transitions, if you have more than one stimulus in your frame, you could use them all. For simplicity, it's probably better to stick with just one. And show the display if you wanted to. Now, the holding potential can either be controlled from here. It can also be controlled from the membrane toolbar, which we can position anywhere. And because it's showing the access resistance here and the membrane resistance, and we can check the box just to show the total resistance. We could. Okay, and the holding potential, which can be adjusted if we wanted to. I should say, if we were doing, quite often you want to switch between voltage clamp and current clamp. And the quickest way to do that is you need two configurations, one for the current clamp, one for the voltage clamp. But you can use the sample bar. If you're in the sample bar and the sample bar list, you have a list of configuration files, and we can just add a configuration. So you just select a configuration you want to add. These have already been added, and they appear in the list. Each one can be given its own label. A comment will appear when you hover over the button on the toolbar that will be created. So here we have, this is the sample bar that I prepared earlier by adding the configurations I'm using. And you can see you can switch straight to current clamp, and it sets it up immediately. You can even configure it so it starts sampling immediately should you wish. And or you can go straight to voltage clamp as quickly as that. One thing you have to be careful of is that you have to remember the amplifier itself will probably need to be reconfigured for the different experiment types. And unfortunately, we can't control the amplifier, so the amplifier has to be set manually by using either multi-clamp commander or just by clicking the switches on the front if you've got a different amplifier type. So that's the basics of sampling. I will come back to a little bit more about sampling when we do a dynamic clamp setup. I should mention a little bit about the leak subtraction. It's an analysis technique which can be done online or offline. Documents, that standard file which is supplied with Signal to practice with, and the right one. That's after it's been subtracted. The one we want is test. Yeah. So this file contains, let me show all. You can see we've got a set of stimuli which are increasing in amplitude as we step through the file. And then at some point, your threshold is reached, and we get a response from the cell. And we probably want to measure that response, but it's got the leak there as well. We want to remove that. So what we can do is we can build up essentially a conductance curve, which is which allows us to calculate how much leak would be generated for a given size of stimulus. And the way we do that, we got the voltage and the current. So we divide the voltage by the current, or possibly the other way around, to get the conductance. And then when we do get a response from the cell, we can multiply the conductance curve by the size of the stimulus to know how much leakage to subtract from the response from the cell. And I did have to talk about this on the analysis talks I did a couple of weeks ago. It's a very standard technique. And let's first look at the basic idea. So the response channel is channel 1, stimulus is channel 2. We need a time at which there's a baseline. This needs to be before the stimulus, so we can know we're going to be using this to measure the height of the stimulus. The baseline time, let's look at 5 milliseconds, say, the pulse, so we'll pick a time that's in the middle of the pulse, 40 milliseconds. Measurement width, so how we're going to average these readings over a certain time range to minimize the effects of noise. So 10 milliseconds is pushing it because we're encroaching on the start of the stimulus there, so we'll make that a little bit smaller. Let's put 8 milliseconds. First frame for leak will be frame 1, and I believe the last frame for the leak is frame 5, so that's the last frame before we reach the threshold and the cell started to respond. So we'll make that 5. Baseline for correction. We basically want the baseline on the response to stay at 0 after we've subtracted out a leak. So even if that's drifted in the meantime, we want to offset the results so that the baseline remains at 0. And count excluded frames. So we're going to form a leak from the first 5 frames. But if we take to process only untagged frames, and one of those first 5 happens to be tagged, then it poses the question, what do we count as first 5 frames if we're not processing one of the first 5? So we normally would check that so we stay in phase with what's happening during the sampling, or what did happen during the sampling, depending on whether we're doing this online or offline. And in this case, if we've excluded, we've said tagged frame 3, we would still only go up to frame 5 to form the leak from. We wouldn't say, oh, we've not processed frame 3, therefore we'll process frame 6 to make sure we've got 5 frames in our leak. We probably don't want to do that, so we check that box to make sure that we stay in phase with what we were doing when we stimulated. And we say new, and then process. Let's process all the frames here. You see that the capacitive transient is all but gone. The leak is almost all gone. The leak subtraction method does assume that the cell membrane obeys Ohm's law. Obviously, we don't always quite do that, so this is not always perfect, but it's pretty close. And we can go through and you see there's a little bit of capacitive transient left. So that's leak subtraction. There are other ways of defining which frames to form the leak. If we use PN, then the leak is defined in a cyclical manner. So you, for instance, you might form a frame from the first 5, or leak from the first 5 frames, and then subtract it from the next 7. and then you'd form another leak from the next 5 frames, and then subtract that from the next 7 and keep going. So you set up an experiment such that you knew you'd be below threshold for 5 frames, and then above threshold for 7, and then below for 5 again, and then above for 7 again. And you keep going in that manner. So that accounts for any changes over time in the membrane resistance, the quality of your seal, etc. So it's useful if you think there may be a drift in the amount of leak you're getting throughout your experiment. PN stands for positive negative, because you can use a negative pulse to ensure that you don't cross threshold when you're stimulating, and the software spots you're using a negative pulse, and the calculations all still work. The other way we can do it is to use states. So whenever it encounters a frame with a particular state, it knows to use that to form the leak and subtract that leak subsequently from any other state of frame that it encounters. I can talk a little bit about single channel analysis. The simplest single channel analysis we do is to use a simple threshold crossing for to form an idealized trace. And just delete that one I did earlier. And that one. So here we have this is very simple single channel data. If I look through it, it's actually got 2 channels in the patch. So if we want to do an idealized trace on this, we'd have to say, well, below a certain threshold, the ion channel was closed, so there was no current flowing, and above that threshold indicates that there is current flowing, and therefore the ion channel is open. And obviously there are 2 levels to this. There's an upper level here which would indicate that 2 channels were open in the patch. And if I then go to analysis and I do open close times, new idealized trace, threshold, I can do the full width of this frame because I don't have any baseline drift here. And I say open above, so I'll say it's open above, and I'll put cursor 2. There's a clear threshold. It needs to get above cursor 2 in order to be considered opened. And if it to close again, we can actually give it a separate threshold. By doing this, we minimize the effects of noise. It's quite often I've seen single channel data where the noise occupies half the distance between the open and the closed state. And when that happens, it becomes impossible to put a single threshold in to indicate above or below this is is open or closed. So by having 2 thresholds, we can eliminate that problem. Bear with me a second. We're having a technical issue here. Okay, really good. And the base level, so it needs to know which particular level is closed. So we're going to, in this particular one, we're very lucky that there's absolutely no leak That's probably because this is simulated data. But yes, we got base level at 0. We could have put another threshold on the closed state to indicate that's where our base level is. Transition points, sometimes if the data is quite heavily filtered, the transitions between closed and open will not be vertical. They will slope quite a bit. And if your data is noisy, you could, during that transition period, it could cross one threshold or another several times. So we have a transition point, which is a number of points to skip ahead by before starting to look for more threshold crossing. Baseline track, as you go through your data, the closed state may shift, and by averaging what the value of the closed state is, you can move the thresholds relative to that closed state to maintain the same spacing from the baseline as the baseline moves. Again, this is simulated data. We don't need to track the baseline. And interpolation, obviously this is discrete. This data is sampled at discrete points. If I zoom in on a single transition, you see we've joined with a data point here, and the next data point's down here. And you say, well, okay, it's going to close when it crosses threshold 1, which is here. And you say, well, where did it actually cross the threshold? When did the closing actually happen? Now, with no interpolation, we'll say, well, it happened at the next data point. But you can also have linear interpolation, which says, well, it crossed between the point before and the point after, and it will work backwards to say, well, the threshold was either crossed here or halfway between these two thresholds is the point where the transition actually occurred. So this can be slightly more accurate at timing your channel opening than if you were to just select the next point. Multiple level, we're going to look again. This is multiple level data. You've got 2 channels in the patch. So by doing that, what it will do is it takes the distance from the baseline to each of the thresholds and multiplies that up to get the next set of thresholds for the next level. And then again for the next level after that, and again for the next level after. You can have up to 6 channels in your patch, and it will still correctly identify the transitions. Analyzing it subsequently might be a bit tricky with 6 channels, but nevertheless, the software will cope. An outward current, so we're going to say that a more positive current indicates transition towards opening, whereas a more positive current with an inward current would indicate a transition caused by a channel closing. And if I say new and process, you can see it's draw on an idealized trace on top of the raw data. And this can now be analyzed. One of the analyses we can do even before we fit an idealized trace is to do an amplitude histogram. So we're going to look at the amount of time spent at any particular amplitude in the data. So we're going to have amplitude will now appear on the x-axis of the result, and time will appear on the y-axis of the result to indicate the amount of time spent at a particular amplitude. And when I build that histogram, you see you typically get a number of Gaussians. You'll get one for the closed state and another one for each of the open when n channels are open. So we've got one channel open there for two channels open there. And we can subsequently fit Gaussians. I did most of this the other week in the analysis talk. Just briefly fit Gaussian curves. I'm just going to fit one Gaussian, having zoomed in on the bit I want. So there you go. It fits the right-hand edge of the bin. If you wanted it to the centers of the bins, you'd have to add half a bin width to your mean value from your Gaussian. I did fit in some detail a couple of weeks ago at the advanced analysis talk, so I won't go into too much detail there. Other analyses we can do with the open-close times, we can do histograms of the amount of time spent in a particular state. You see each of these horizontal portions of the idealized trace has a number of flags associated with it. So if I want to look at open times, we'll exclude close times, first latencies, truncated measurements, anything flagged as bad. Do a process on that. Now that's done with the logarithmic axes. Doesn't look like that as exponential with the logarithmic axes. That's one of the options we can use to. If we look at that again. We say use log binning. Log binning is quite a common technique used in plotting dwell times for idealized traces. Don't use the log binning, and you get a linear axis, and you get a more familiar exponential decay, which you could then fit an exponential to or a double exponential to. We also have various burst analyses we can do here. Burst durations and that's, well, there are other measurements, other ways of generating idealized traces. Let me just speed up a little here. We have a different data file to show you. Scaling analysis is a much more powerful method of generating an idealized trace. Again, this needs right, let me delete that. Okay, so here we've got another single channel data stream. And as you can see, this has been quite heavily filtered, and there's a closing here. This is, we've got the closed state at the top here. It opens as it drops down. Here it's closed. It's closed so briefly that it's been filtered out. And if we try to put a threshold on that, it would be missed by the analysis. So what we can do is select an area baseline. That's an open close time analysis to baseline measurements. And we want to analyze the area we've got on the display. We get a set of levels which are then going to be used in subsequent analysis. So once it's done that, we move across find the appropriate bit. There we go. Zoom in on the first opening here. What we then need to do is to put some cursors on this. So I'm going to put a cursor on the baseline, roughly. Another cursor on the open level, roughly. And another cursor which will be just below the noise. This will be used by analysis to identify potential openings. And now I can go to open close times, scan method of new idealized trace. And we got channel 1, we've got one channel in this file. And we're going to start at X low and end at X high. It's recommended that you don't try and do too much at once when you're using scan analysis. And the baseline is cursor 1. We're going to track the baseline this time. We're going to, this is an inward current. So we want to open below cursor 2, and the open level is cursor 3. Filter cutoff, I believe this has got a 6 kilohertz. This is the 3 dB level for the filter that was used. I think it's 6. We'll have a look and see what happens in a moment. This is something that you would have set once you on your amplifier when you were capturing the data. We're going to avoid sublevels. That doesn't eliminate sublevels from the idealized trace, but it does produce fewer of them. Now there are a whole load of other parameters to do with the way in which it identifies potential openings and closings. I won't go into that at this stage, but just be aware that they do occur. That's the new, and now the process. Okay, so now this looks terrible actually. So I've probably got the wrong settings in the cutoff frequency. We change that. I'll come on to it later. Let me do a fit of that. I look at the event details. I can do fit visible, and that produces a least squared fit. What it does is it says, well, if we run the idealized trace through a Gaussian filter, what shape curve would we get? And it's now turned black. What was a blue trace is now black. And that indicates what you would get if you ran the idealized trace through a filter with the characteristics that were specified in the analysis. So with a 6 kilohertz cutoff frequency, the Gaussian filter, this is the shape that will be produced if we ran the idealized trace through it. And the idea is to adjust these transitions to get it as close as possible to the observed data. And we can actually edit the idealized trace as well. If we decided we didn't want these extra transitions, we can merge and do fit. That's probably more believable. You might want to pull that up to the closed level and fix its amplitude. Assumed amplitude. So hopefully that will. No, it doesn't like that. It doesn't. Anyway, that gives you the idea of how the idealized trace formation with scan analysis would work. And I can go next and look at the next transition, and then do a fit on that one, and then so on and so forth through the file. Each time I can check what it's done, edit the idealized trace, rerun the fix if necessary, and build up an idealized trace by that method. Obviously, this is a lot slower than using a single threshold or double threshold crossing method, but it is way more accurate. It really does check that the idealized trace matches what the observed data is. And finally, I'd like to just do a quick demonstration of dynamic clamping. If I show you what I've got set up here, this is current clamping technique. You see I calibrated the DAC in picoamps. I told you I'm doing a current clamping, and then we got this dynamic clamp button we can press, and we can add models. So there are all sorts of models we can add. The Hodgkin-Huxley models are essentially solutions to differential equations involving the membrane potential. And then there's a variety of other synapses essentially are conductance as a function of time, and they can be either predefined functions of time, or you can define your own and have an arbitrary shape of synapse conductance that you can create with a text file, just a list of numbers in a text file. We also have leak, which again can be either with a number of known leak types or a user-defined leak. So the conductance of the cell is an arbitrary function of the cell membrane. If I run this model, I first of all need to do some adjusting on the amplifier. I think I've currently got it set in voltage clamp mode. I need it in current clamp mode. To connect the amplifier output previously I've been using an RC circuit there. So when I run now, okay, probably got the gain on the amplifier way too high. That's better. So what I'm actually doing, if I turn the dynamic clamp off, all I'm doing is applying a square. So this is the stimulus. Applying a square stimulus pulse. This is a slightly dodgy amplifier, I'm afraid. This was a scrap amplifier that we were given, so it's behaving slightly oddly here. If you do want to do dynamic clamp, you do need an amplifier which has got a bridge balance. Unfortunately, this one hasn't, which is another reason why it's behaving slightly oddly. You also need either a power 1401 Mark II or Mark III or 3A, or a micro Mark IV. The earlier micros are too slow to do the necessary online computation needed to make dynamic clamp work. Turn the models back on. What you can see is happening is that despite having just a model cell connected, what I'm getting out of it are action potentials. So you can use dynamic clamp to add this functionality to, if for instance you'd applied a pharmacological block to your cell, you could reintroduce the conductance from particular ion types. Or similarly, you could subtract conductances for particular ion channel types by adding a negative conductance. So we've about run out of time. Do please ask questions if you wish. Always happy to answer questions. If anybody has a question that they think of later, then do email it in. We on softhelp@ced.co.uk. Everybody's in stunned silence. Let me just illustrate something whilst we're all having a think. If I show you some action potentials, sampled before, these are real ones, not simulated. That's not it. That's the virtual channel. And we could standard display. There we go. Just delete some of these. Channel numbers back on. Okay, we'll just look at this channel. We got action potentials here. And if we can measure where these peaks are, so we do measurement, we can do measure to data channel. We can measure to a real mark channel, finding peaks with cursor 0 on this channel. On the right channel, and across the full width of the channel, and amplitude of each peak shall be 20. And not too worried about the width and the minimum step. They're sufficiently far apart that they're not going to get confused with each other. If it was very noisy, we might want to skip ahead and have a minimum step size there. This is very clean, so it should work. And we want the value of the data point on channel 1 at cursor 0. We don't want any, we want to average the amplitude reading over any sort of width, because if you do that on a peak, you will bring down the amplitude inevitably. Hopefully, process that. And measured the wrong channel. Let's try that again. Measure to data channel 2. There we go. So here we see the heights of each peak plotted on a separate channel. This is a memory channel which will be stored on disk, but not in the data file. It's stored in the SGRX file. Let's put that in a bit. There we are for each channel. Now, what I can do, if I could figure out how to get the channel numbers to show. is put these on top of each other. Something strange is wrong with this channel numbers. Here we go. So now I can drag that down onto top of channel 2. So now they're both sharing the same set of axes. I need to lock the axes together so that they really are taking, they're both plotted on the same axis, even though at the moment this is plotted on an axis which is hidden behind this other one. If I lock the axes together, then they'll both be plotted, so they'll both be read off the same axis. And that's very embarrassingly not worked. Where's that gone? Ah, I know what I've done. As you can see, the readings on here are way different to the amplitudes on here, because although I've correctly identified the peak times, I've gone and taken the amplitude readings off a different channel. Let me delete that one. And that needs to be 2. Process. Now when I drag that on top of there and lock the axes together, you can see how the measured points line up with the peaks in the original data. Next step. I think my data. Well, unless anybody has any questions they would like to ask, as I say, you can always email them. We're about out of time. You're welcome to join us next week. We'll be doing some worked examples, some TMS probably, and maybe a few other patch clamp examples. If there's anything you particularly like us to work through next week, again, email us and we'll see if we can incorporate that into the talk. Otherwise, I will see you all next week. And thank you all for coming.